So what am I going to do today? I've got my Z8S180 project board here. I got a Pi, the FPGA, the CPU card. I'm going to try to port from the state that it's in right now, last time I left it on GitHub, the Z80 Retro CPM BIOS. I want to be able to boot up CPM on this thing in all its glory, okay? Including the SD card driver, which I think is actually going to be the easy part. The hard part's going to be the lousy serial port, I think. I've never used a 180 before, so I don't know. It should be easy to configure UARTs, but it's always a pain in the butt with enable and the not enable, interrupt, inhibit signals and stuff like that, and the crappy manuals, by the way. So hopefully there's enough there for me to get this done. Let's find out. Forgot to power up the bench cam. Please work. Yeah, if I don't edit this, there will be boring parts. Better watch this at double X speed on YouTube. Okay, that's booting up. We're good. Let's make it happen. A big thanks to everybody who's helped me out, especially the VIP patrons shown here. Thank you very much. All right, the first thing we got to do is decide what manuals we're going to base this stuff on. All right, here's the Z80 family MPU user manual. This is the key right there, the UM005-004-0918. This is a user guide type of thing that looks like it was created by an intern trying to learn how to use Interleaf for the first time. We also have the data sheet, which is a preliminary specification. What document is this one? There's a couple of these with different variations of these numbers. DS006-002 ZMP0200. That is the data sheet that I'm looking at here. You can tell the difference between a data sheet and the user manual because the data sheet information density is vastly superior to that of this user manual that I'm scrolling through right now, where they waste one sheet per paragraph, so you got to scroll forever and a day, and this has got double columns. All right, so there's the takeaway there. If you get disoriented, that's what I'm doing. And the errata. Hopefully I don't get cut off of YouTube for saying this word, which is the proper word for typographical errors. This goes back to early printing press years. Okay, so probably even to written work. I should look that up. Anyway, I'm looking at OT001400 ZMP0599 on this one, okay? The reason you want... Okay, first of all, this chip is like, what, 30 years old? If you got a 30-year-old chip that does not have a manufacturer's errata, errors, whatever they want to call it, a document that outlines this stuff, then they don't respect you, and you should not respect them. Go find another source. Okay? I'm just saying. Nothing's perfect. There should be disclosure of that which is imperfect. Okay? All right. Now, the reason we really need to look at this for today is because the main thing I want to use, the hardest thing I'm going to have to overcome to do this, I believe. Surprise! I'm probably going to be wrong again. But I think the hardest thing is going to be this serial port. And if you read these notes about what's wrong, part of it is the serial port. So they say there's something wrong with the CSI module. I'm not going to use it, don't care. When stat 1 is 1, bit 5 of that should reflect the state of RT. We're not going to use flow control, so even if this applies to the ASCII, which is what they call the serial port on this thing, with the sky, this I'm not going to use CTS, which I believe is what that is referring to on the port that I'm going to use. This is a little more interesting.
When a receive overrun condition occurs, the ASCIIs on this thing suck. Oh, I'm sorry, I'm just paraphrasing. They don't put any more characters into the FIFO. Why? Because they want to be weenies about it. I have to clear the ERF bit in Control A in order to allow more characters to arrive. So when we're just clowning around, I usually just let the thing fly, and if I don't read them, I don't care, and throw them away. I don't check. I don't care. I do not care. We can't do that with this because the whole UART is going to shut down. The receiver will shut down if I type away and it gets characters when the software's not reading. And that is definitely going to happen when we're debugging. And I'm just thinking out loud here, it's definitely going to happen when we're running CPM too. This is just stupid. All right? I don't know how they didn't even notice this. But, you know, stuff gets by all the time. I'm sure I've committed far greater sins. On the other hand, we're going to need to be very careful about this. So what I think I'm going to do is gratuitously just write 0 into this ERF bit every time I'm trying to read the status. Because, and I'm thinking ahead, when CPM is running, we're not going to use interrupts. We're not going to enable anything fancy. Just make it go, all right? And the Z80 Retro runs in that mode roughly anyway. So this is, I'm like, I come to the realization just like last night or the night before, this should be doable in a single shot. So anyway, what happens in CPM, no interrupts. All right, where am I going with that? If you're not following, where I'm going is that when it's waiting for a command to be typed in the keyboard, it's spinning, reading bytes, not going to drop anything. Let's say I run a program, plays a video game or something, and I'm using the joysticks, like on the Retro, and you're driving around a Sprite or something. You're not reading the keyboard. You hit a couple of keys, you're going to get an overflow, and then from there on else, for the rest of eternity, the UART's seized. That's why this is important, okay? So we're going to, when the time comes, we're going to gratuitously read this so that we don't have a stuck UART. Oscillator power drive is 33, blah, 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 blah. We're not using it, don't care. I/O pins, weak latch circuits. Yeah, okay, this is a nice one, actually. They added these, okay, so this has weak latch circuits to prevent excessive current draw by the receiver. That's probably been there since day one. People had problems, I suppose, if they use a 100K pull-up or something. Even 15K is kind of big, which I used on the Retro, I believe. That's, as they say in here, you need to be no weaker than 15K. In other words, no bigger than that. Otherwise, you can't overcome this internal weak latch circuits. Basically, they got a pull up or a pull down. Yeah, they have holding latches and stuff. We talked about that when I was talking about logic families and stuff like that. I think I mentioned it. Some chips have special circuit that will, on an input, hold the input high or low if you drive it high or low and then let it float high impedance. It stays. It has a hold circuit. And that's what they're talking about on here. In order for that to work, it has to draw a little bit of current to overcome the hold. So therefore, if you're going to put pull-ups or pull-downs, you need to make sure they're, 15K or 10K would be fine. All right? Additional information can be found at this broken link. Okay, so we'll salt that one aside for now and keep in mind that the whole thing is probably going to seize up. We can test that. It's going to be easy to do. Okay, so this is the data sheet. And I'll show you. Okay, so I flipped through these this morning to make sure I had the right manuals. And it's obvious that we're going to need to read both of them at the same time. Because the user manual, these both excel in their own way. What you really want is, in my opinion, what I really want, I should say, is I want a hybrid of the two. I want the engineer that wrote this to go back and fix all of his idiotic typographic errors. And I want whoever did this to clean it up a little bit and put it back in this format over here. so I can see on one page more than one paragraph. All right? Now, the reason we need to see these both is because they have a different set of typographic errors in each one. And once you read them both, they make sense. I take that back. They come closer to making sense. Before we get into the details of the UARTs, let's look and see why I think that's the only thing I have to care about. So here's the retro schematic. Whatever this version 4 or whatever, the latest, greatest, super awesome schematic, right? Was it Rev 440? Okay. This is the CPU, SIO, CTC. What do? CPU, we got to have a CPU. This is going to be our new S180 is going to do the job of this. Inside the S180, it includes UARTs, so we don't need an SIO. It also has baud rate generators and timers and things, so we don't need a CTC. So these 3 chips we get in one box. That is what we get out of the Z8S180, okay? Now, if we want to run the software that I designed to run on this board, we need to make sure that it has a GP input, a GP output. We don't care about the printer. I don't care about serial. I do. What I'm going to do is hook this up to a 340. I had a video on testing that chip on my bench. I dug through some boxes, found it. So we don't need this. I can hook it directly to a USB converter and plug it in and directly connect that way. So this is replaced by a USB adapter. We don't have a printer. I throw that away. What does that leave us with? Our RAM, our boot ROM. These two I already went over when I was evaluating the board and verifying the design was okay. No problem. I actually was able to boot up the S180 and run code out of memory inside the FPGA that would play the role of this flash. So we know that's going to work. We already know how to do it. In painful detail, I went through that earlier. We know the SRAM works because the inchworm demo in the video, the last video I did talking about that project, this project, with the inchworm, we tested our ability to talk to the SRAM. This flash select logic we can implement in the FPGA if we even care. The bank select logic we can also implement in the FPGA if we care, and I say that because if we care about both of these, ultimately the Z8S180 has a banking system built into the CPU, and if we use it, we may not care about this shadow flash thing because the S180 can address a megabyte of memory space. So we could, if we wanted to, leave the flash in all the time. And then, because we only need a couple K to boot out of, and then the SRAM can sit in the rest of it, and we can use the memory bank stuff in the S180 in lieu of this, because I can just map RAM over where the flash is. We'll talk about that some other time. Today, we might go ahead and do this anyway. And the reason is to keep it simple so we don't have to play around with the MMU in the S180. This, I'm not going to do at all because we're not going to do any banking. We don't do a lot of banking in the retro project other than using it for like disk cache buffers and things like that. So again, we're going to cut all the stuff that's unnecessary out of the first go. So this is going to be gone. I'm going to have 64K of memory addressable. By default, when the S180 boots, it maps the static RAM, or the memory bus, I should say, into the from the perspective of the CPU into the 64K that it sees. So I can implement this with like a couple lines of code in FPGA, along with what we already did with the boot ROM and the RAM that we played around with last time. Okay, so we'll figure that out when we get there. These two I/O ports, I think, is the key to making this super simple. Look what we got here. We got a decoder that says when I read and write various ports, what's going to happen. I'm going to talk the CTC or the SIO and all that junk. That's built inside S180, so we get that for free. We only have to worry about these if we want to talk to the SD card, which we'll do soon enough. Once we get the serial thing going, we'll want to be able to read the SD card. And I honestly think, I know, if we take the FPGA and we watch the address bus and we watch it for I/O operations, we can create inside the FPGA an input latch and an output latch. And if we do that and we connect up bits of the latch that we implement, in an always block with a pos edge or whatever, a synchronous circuit in there, we can map data bits to the SD card. So I think this is going to be super simple to hook up the SD card so that it presents itself very, very much like it does in these two latches. This is not going to be a speed demon, but it'll run the exact same code, potentially with zero modifications. So that would be super awesome for the SD library. Clearly, I got to mess around with the serial port and the CTC and some of the other things that are in the BIOS, but not the SD card, which is going to be the worst pain in the butt to do. So I got super excited once I realized, just hook up these bits like this, those like that, and all the bit banging code will work fine, and it'll run probably 2-3 times faster because the chip is so much faster anyway. So that's what that's what we're going to do here. All right. So what am I going to do? I'm going to take the CPM code from the retro. Then I'm going to take, I got to boot up my Pi, and then I'm going to take the Verilog example code that walks through the SRAM and evolve that into booting the flash boot code from the retro project. Okay, so let me power up. Where's my camera? So the way I do my bench camera is I have a Pi. What is that one? That's Pi Cam 1, I think. Why can't I? Oh, lovely. Oh, maybe you got to log in as Pi. There we go. I have a little script in here, and I run cam1.sh, and it fires it up and spews all over my screen, and I bury that off somewhere, and I can see from the preview monitor, things are looking okay over there. Let me swing around the mic. I have no idea if this is going to sound any good. I'm not going to worry about it. I think you can hear me. Ooh, I got to turn on the... I have to capture the video. So that means I have to, what am I doing? Video. John's Basement stuff. Here's a bunch of videos. Here's this one. Up here are some scripts. Record iCam 1. Yeah, I could do a better job at automating this, but I don't care. PC1 is what I usually call that file. Oh, that's not good. Now I need to make sure the other video is okay. What it did is it screwed up because they're both trying to record from the microphone at the same time. Let me hack this script so it doesn't do that. I'm sure this is an error and the other one's still recording, but I'm going to restart it just in case I lost audio. Okay, that one's back. What do I need to do? I need to write a new script or just hack this one and comment out the audio part of it. So here's where I record. I just stream the FFmpeg stuff from the Pi. I should do a video on how I do that. Somebody asked recently about it. And this is how I record my audio. So I'm going to do this so I remember which line I commented out. This one. All right. Now when this runs, Pardon any swear words in here. I don't think there are. I try not to put them in my comments, but sometimes it's just so deserving. Somebody writes an app that I'm forced to use in a way that really stinks. Okay, there we go. Boy, is it going to work right? Because what this does is it starts two processes, runs a wait or something. So FFmpeg runs in the foreground. Q will stop the audio. Whatever. I don't know if this is going to work. I never run it like this. Okay, here we go. Take two. That was a critically important thing that I checked to save those files. I used to blow these away when I was recording. You got like an hour-long one take of something. Oh, you don't hear enough cursing on those days. Okay, what do we got going on here? Did I boot up my Pi yet? No, I did not. Zoom this out. Whoop, that's the iris. Okay, here we go. Here we go. All right. I don't know how far out I can go. This lens is not designed to be used this close. Usually takes a little while. There's glare. This has a thing I usually put on here to kind of block the glare. That's a little better. That's the best you're going to get in this short amount of time. All right, so here's the USB adapter from my other video. Bring the microphone over here. Let me help a little bit. Okay, so we've seen this all before. The difference between what I did last time and now is I pulled this wire out. It used to go up in the pin 16 or wherever up here. And this is the 5-volt line from the USB. I pulled that out and stuck it in here to keep it out of the way. And instead, I put these jumpers in here and run it over to the red rail, which I'm going to use to power the whole thing off of 3.3, which is one of the modes they allow you to do. In the manual, it says that you can either connect the whole chip up to 3.3, or that you can put 5 volts here with a bypass there, and it'll generate its own 3.3 for the inside circuitry and stuff. But if we're going to talk to a 3.3 volt port, the serial port on my S180, this is running on 3.3 volts. We got to make sure everybody's got the same power, right? That's all I'm saying. So I'm going to put this off to the side. These are the data lines, and I'm looping them back to make sure this thing works. I just stuck this in there this morning. All right, so what I'm going to do here is I've got the black is ground, white is going to be hot, and in the corner of the FPGA board, I got 3.3 on the end and ground in there, so you can see, hopefully, that I will hook this up right. All right, that looks good to me. It's on the end. And when I'm yakking, I have to stop and double check. Because, you know, if you put this stuff in backwards, some chips are not going to survive. And I'm not, again, you know, always with the cursing. I'll get my videos will get delisted. Or at least I'll end up with no advertising. Because, you know, I'm making so much money on YouTube. The day it goes over $3, I'll be surprised. Okay, we got a loop back in here now. So what I'm going to do is I'm going to run the USB adapter. I'm going to power the whole system up, but I'm going to ignore it just so that I can take the Raspberry Pi power and run this loop back on the USB board here. So I need to make sure it's working. I got the right pins and stuff like that. Okay. Okay, I don't need this in view. All right, but we got here's a plug. I can plug in the Raspberry Pi. Hopefully, nothing will blow up. You can see the inchworm. This is the same code we saw last time. Nothing's been done. Oh, wow. Okay, I need to make sure all the files have been updated in the repos on there. No big deal. It's probably done booting. Oh, I need Ethernet. Here's the Ethernet cable. And I can hear dogs barking. All right, let's try it out. Oh, on the screen, and I can clothesline myself with my headphones. Alrighty, here we go. Minicom. USB 0. Alright, well I can see what I'm typing, but that don't mean diddly squat until you go back over to the loopback and disconnect it. So we can get a positive confirm that it's not working. Okay, so that is number one most important thing. Yes, I'm connected to the right USB port. And two, it does appear that the serial data is going out and coming back and all this other fun stuff. I have no idea what bit rate. 115.2. That's probably not going to work. As we'll see, the bit rate is going to be our biggest problem with this thing. Because I don't have an optimum oscillator clock on there. Now we can get in and use the PLL and the FPGA and generate pretty much anything we want, but I haven't talked about that in the FPGA series. Let's see what we can do without it. It's easy enough to use once you know how, or you know what options to choose. So we may go there if this gets too annoying. But let's go have a look-see. All right. There's my pie. All right, so I logged in earlier today, and I made sure that I had my Git repos all pulled. All right, in case I had, watch GitHub go down in the middle of the day, or I lose internet or something. At least I can still record, right? So this is what? This is the Z8S180 project. We've seen this recently, and inside this directory, there's this SRAM. This is what we're going to make run the boot code that I wrote for the retro board. We're going to port it over to this thing and see if we can get it to go. This is the main thing we're going to hack. I think the majority of our time will be tinkering with that. And what we're going to do, what are we going to do? Do we need these Verilog examples? No, we don't. Well, we might. But these are here because this is where I record my regular Verilog videos. What do I need to do? I need to go get the Z80 Retro code from the Retro repo. Here we go. GitHub. Get 'em hub 'em. Where's my retro? Right there. There's the board. Software project. There we go. There we go. By git clonage. I GIOT. That's not right. Dang it. No, no, no. I should have never done this. I'm sure many people have been peeved off about it. I won't do it moving forward anymore. Not for general public repos. I've got to think when I'm talking when I do things like that. Okay, what did I do wrong? Anybody? All right, so here's the thing. When you download this, you need to read the doc. Since I decided to do something stupid and put two repos in one with a recursive inclusion, okay, you need to do this. which means go out and get what I just got myself, plus the other repo that's involved, which is the CPM repo itself, which is now officially, formally made freely available, at least according to some random letter I downloaded off of the internet, which I believe is true. As the Computer History Museum mentioned it, and some places that might have looked into it a little more than I did. Okay, here we go. Here we go. The boot right there is what we're looking at. This is what I want to get running on the Nouveau board. All right, that's all. Just this. No big deal. So, what's our Achilles heel? It's going to be these two modules. I walked through all this in great detail over recent years. This is just software. That's just software. This is just software. And this is going to be the thing that does the bit banging out these GPIO ports that we was just looking at. Right down here, okay? The SPI code is what interacts with these two latches. And I'm going to leave the bit banging in there because the code's already debugged and done. And it will work as long as we have bits set up somewhere in some latches that connect up to the SD card. And that's what's going to be so cool. That's going to be awesome. Okay, so what else is going to go awry? The IO address maps and the memory address mapping will be different, okay? So, honestly, we can diddle around with a couple of these config files and fire it up. Probably. What do we got here? This bank turn on and off stuff with that latch. We can make this work. I might as well. Why not? Just for fun. It'll be a good, Verilog example thing. In other words, do this up here so we can turn on and off this thing. That will make the Nouveau board look a lot like the retro board. And we won't use any fancy stuff from the S180 in this first attempt. All right? So what does this thing really need to do? It tries to copy itself into RAM, turn off the flash, and then it, where's the RAM stuff? There's a little note. There it is. Copy itself into RAM, flip over to RAM mode, jump to light speed over here, set up the stack pointer. We don't have a CTC, so we don't need to do that. This is the thing that will initialize the ASCII instead of the SIO, and then we're going to try and print a message. So printing a message is my number one priority right now. That'll allow us to debug everything else as it goes. So, what does that mean? That means that what I'm going to do, we don't need to have all of CPM in here just to get the darn thing, the serial port thingy. Let's copy SRAM to, let's call this the ASCII. So this, make clean, is where we're going to test our ability to operate the UART. Example of putting a CPU and running code on the RAM 4K block. So we're going to have to do a number of things here. We're going to have to be able to run out of more than one RAM blocks because I think that the boot code is 2K or something. So we're going to need at least multiple of those. That is in multiple RAM blocks in the FPGA. Now, I honestly think we get this for free. We just say, well, I infer a RAM and make it bigger, please. Make it so. You know, the Captain Picard style thing, right? Make it so. I think that my point is that the synthesis tools will figure out, oh, I'll get 4 of them or whatever it needs, and gangs them all together until we run out and then it complains. Assembled into binary and then loaded into the FPGA block. I can not say this anymore because that's part of the other example, really. Well, I can leave it in there. It's certainly not false. And impatient people like myself might just jump in here directly and not realize that otherwise. adding a register inside the FPGA that latches the value. See, we've already done the latch for the output. Awesome. We just make another one for input, and we're in like Flynn. This useful when combined with the LDIR, blah, 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 observation, the only way to get, okay, this is going to go away. This example is an example on how to initialize and use the ASCII. And or it'll be an example of how not to do it if we can't get it to work right. So what does that mean? I suspect we don't do much here. This hooked up, as you recall, the control lines and stuff from the CPU to the RAM. What's this doing here? Oh, I talked about that, yeah, when I walked through this last time. The RAMs in the ICE40 have to run in synchronous mode. Therefore, you have to give them a clock. We'll look at some timing. I actually looked at this before. We don't need to talk about this anymore. It'll come back to haunt us again later anyway. I'm going to just kick that down the road. One or the other of these will work. And I talked about that when we were doing the board testing and checkout. Reset. What's this doing? When the CPU is reading from the low, then enable from the RAM, else try state the bus. Oh, okay. So now we're going to need more than 512 bytes. And the address is less than... Oh, that's easy enough to fix. Let's make it 1,000. So that's going to be 4K. In the low 4K bytes. All right. That should give us enough room to play. And now we're going to... Oh, boy. That means that our address bus... ROM data, ROM output bus, what's this thing, TP? Oh, those, oh yeah, that was right. I connected these up to a bunch of pins on the bottom row of the FPGA so we can look at them on the scope if we need to. This slows down the clock. This allows us to run faster. We may play around with this a little bit if we have to change the clock speed in order to get one that is compatible with the UART. And this is the thing that lets us write to the LEDs. Whenever the CPU writes into FFFF, that last byte of memory, it can put a pattern on the LEDs. That's kind of cool. Fine. Where's the RAM? Where's the simulated RAM? Memory RAM. There we go. Now, okay. So here, okay, there you go. I'm sending over address 0 through 8, which gives us a 9-bit address bus, which is a problem. We need more bits if we're going to go. We're going to go to 11. 4K. What's 1K? So the 9 bits is 512. 10 bits is a K. 11 bits would be 2K, and 12 bits would be 4K. So if you need 12 bits, you need to go from 11 to 0. Should give me a total of 12 bits. And I'll put this here too before I forget. If we ever switch these, that'll be a real brain uber frustrato. Yeah, these combine with this down here. And what I should have done is put a local param in here, by the way. And defined it, and then calculated C-log2 to figure that. I'm not going to type all that crap in because it will be here for 6 hours. We're going to be here long enough as it is. So this is stupid. An example of me being a total hack right there. I should have never done that in the first place. Looking back in hindsight, that is really a stupid thing to suggest if you're just getting started in this whole thing. These should have been configurable. What do I need? I need 4095, right? That'll give me 4K. Read in Rambo hex. Gotta have that alignment. Okay. Whew, that was close. That should be fine. Does ROM hex have to actually have the right amount of bytes in it? Did I need to do something special for that? I don't recall. I'm going to go with a no since it only has 78 bytes in it. Okay, so now I honestly think that's it for the FPGA to be able to get the ASCII going, right? You know what? Part of the ASCII is going to be a problem. The part where I don't have a set, I never soldered the header in there. Yeah, I may have to do a little header installation there. All right, what do we got going? What are we doing? We're going to run from 0. Oh, yeah, this is the refresh. And yeah, leave that alone. Don't touch it. Now, what are we going to do? Pad it out and do some stuff. Okay, here we go. Here we go. All right, get rid of this. Okay. We're going to have a loopage. We're going to have a super looper. All right, what do we... Well... Init said ASCII. Welcome to the better part of the day, right here. Frustration begins now. Okay. What do we got going? What do we got? 2 things, yada, yada, yada. Okay, blah, 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 blah. And it can communicate with things. I'm so happy. Key functions, stuff. This is the block diagram. I always get a kick out of when they show like registers that are so overwhelmingly obvious. And why don't they show all the AND gates that that connect up all the signals? My point is they actually show the shift register with a little asterisk. Oh, by the way, this is not programmable, not user accessible. Yeah, there's a lot of crap in there that's not user accessible. The fact that they go bend over backwards to make sure this is in the diagram, I get a kick out of that. Whatever. Okay, so here's the deal. We have a weird clock, and remember in the retro we had like a 1.8 some odd megahertz crystal, and I explained that we chose to have that crystal in there so that when we divided it out with simple, powers of 2, we could come up with standard baud rates. We do not have a weirdo crystal speed, therefore we do not have standard baud rates that are easily attainable in the design of the circuit. We have to do something in order to get a frequency based on the clocks that we have available, which is the 25 megahertz onboard oscillator on the FPGA. Now, we can either convert that to something using a PLL, and like I said, I will resort to doing that if necessary if we start running out of time. Or what we need to do is say, okay, I got a weird frequency. I'll use this baud rate generator, which won't do a perfect either, but it'll get us close enough for it to work. So I'm going to try and go for this thing. It's not available on the Z8S180, or the 80180 or whatever. It's only on the S180 that has this thing. Okay. Otherwise, you have to use the power of 2s that are in here. Okay, what do we got going on here? The transmit shift register. This is all usual junk. What you do is you write bytes into the transmit data register. When it's ready, it puts them in here and sends them out. When data comes in, it shifts it in here. Once they arrive, they go in there. Unless someone is a dingus and and screwed up the design of the UART so that after an overflow, the whole thing seizes up, which is what is the case, as we know. So, but otherwise, that's what happens up here. We got a couple of control registers and a status register. Okay, this is the part that has some creative documentation going on, but otherwise we should be fine. No big deal. Write data into the transmit register, read data from the receive register, and I'm glad we burned up 5 pages on that so that we can write 1 sentence on something that's super critical. Okay, status register, modem control. We don't care about anything at all. We certainly don't give a crap about status on ASCII 0 because I'm going to use ASCII 1. All right, so ASCII 1 is the one I want to see, which is, wait a minute. Sometimes, that's another thing about this. Sometimes they go, oh, it's ASCII register 0. And other times they say here's 0 and 1, and they give you the same section here. Now, these manuals I couldn't figure out why they were organized in such an insane way. It became more obvious over here. When you look at these, this manual, what they do, like you idiots, they go through this and they give you all these registers and they tell you the pins and all that other fun stuff. And then they start talking about, there's the pin descriptions. Oh, here's the architecture. Okay. In the early Corinthian style, we got modes, blah, blah, blah. There's all the stuff about the clocks and speeding it up. We talked about that before when we were trying to see if it just would go. Here we go. Here's the more engineering-oriented one. Same diagram up there, and then a little more condensed description of the registers and their bits. Now, what's going to happen in here, in this manual, what they do, when we get to the status register, receive data, status FIFO, you'll notice that we got the A0 and A1 right next to each other. This one is written in order by address. Okay, I found a hell of a time trying to find things because you've got some registers that have to do with the ASCIIs. Then, for no reason, they define a bunch of registers that have nothing to do with the ASCII. And they're just like, they could be, they have names that like, whoa, I didn't know it had this feature. And it's just like there for no reason. It would be nice if they talked about all the parts of the UART in one section of the manual and not strew them all over randomly. Their organization scheme is by address, not by function. So that was a bit of a brain. That's number one, if you're going to try and read this on your own. It looks like this one and this one are not necessarily ordered in the same way. But you got to be very careful when you're on the art major over here that wrote this one. Here's status register 1 and address 5. So sometimes I bounce back and forth between these two in order just to figure out the freaking address. Sometimes you can do a galactic text search in these documents and just start looking for these addresses if you really cannot find anything. Other problems with these documents is that the fonts that they chose, if you try to search for something like the BRG or the ASCII, it won't find it. Because, the ASCII did work. I don't remember what it was I was looking for. It might be the BRG. When you start searching for these things, because you want to find references to things, you'll find, boy, here you go. I picked two that are fine. This one is the one that had my trouble. We'll get there soon enough. What I'm getting at is that the fonts that they chose, or there might be an embedded space in between two characters that you can't see visually, but it's there in the data. So you can't find it if you do text searches. So be very aware of that. And I was looking around earlier for the BRG, which I call the Berg in the red rough. And I couldn't find them. And it was because some of these things had weird things going on with the fonts. All these like different alphabets from other languages and stuff are cropping up. Anyway, just be wary of that. I digress. So they got the control register A. And, so this one actually gives you it all in one site. This one strews it over 87 pages. But this one has the initial reset values in the same box as this. They'll blow a whole page on that diagram where they could have written the initial values here and made the diagram like this and not make, what is it? 71 pages for this one, and granted it's a data sheet, versus 300 on here. I suspect 50% of the bloat is just space. Okay? just saying. I loved the 80s. The docs were so much better. What am I looking for? I got to configure this stink bomb. What are we looking for? Now I remember what I can't find. It was this dumb. The extension control. Let's see if it's in this manual. It's going to be a long day. You better be watching this at 2x speed on the... Yeah. So what I'm really looking for is #5 tick:6. It's like, okay, learn how to use PDFs, people. Yeah, okay, fine. Pot calling the kettle black. I use LaTeX for a lot of my documents, and LaTeX I don't have this much trouble with it, but it can get creative and in a similar sort of way. This is like really bad though. So like I said, be careful when you're searching, and you'll notice what I did there, okay? So I've run into this before. What I did is I highlighted what I want. I find one the hard way, and then I highlight this, and I hit Control F. And what Control F does is it says, take what I've highlighted and put it in the search box and then search for it. So if you don't know what to search for and you found one, you can use this technique, which has saved me more than once. Okay? This is just, our lives are hard enough as it is without having to remember more rules than the parking rules in downtown Chicago. Go up to the north side sometime. There's like 17 signs on a pole, half of which contradict with each other, and then there's a sandwich board sitting on a sidewalk that says no parking during night games. And they don't bother to say what sport, but usually on the north side they're talking about Cubs games. And if you don't know the Cubs schedule, you get your car towed. It is a wonderful. Yeah, this manual just reminds me of that whole thing. My younger years, you go downtown, you got to be aware of all this. Okay, so I'm looking for back to the beginning of this section here. Okay, we need a control, and then this one doesn't even have the EXT. Oh, this person should be drawn and quartered. What a piece of crap. I say this because the EXT is the thing that you need to use for this, for the baud rate generator. I just noticed this right now. Praise God, I decided to read both of these at once. Also, this manual has a real weird way of presenting all that stuff. What was it? There's a comedy bit. Love or hate the guy. Woody Allen has a very funny bit about parking and driving in Manhattan. And it involves having a moose strapped to your car during hunting season. And Google it. It's a pretty funny bit, and it would not surprise me if it was based on a true story. If not there, certainly in Chicago. Okay. I'm just looking at this in disgust that it's not in the other manual. All right, so the bottom line is we have to figure out what to write into these configuration registers, which is going to be a boatload of fun. And then we'll be wrong, and we iterate 17 times and eventually figure it out. Now, normally this involves a lot of coffee, sometimes some beer, a lot of cursing, and a few breaks, and throwing stuff around the room. So I'm going to save us all that drudgery. Now, there's somebody that chimes in every now and then on the Discord for the Z80 Retro series, and I noticed that person responded to this email from this guy. I was Googling around saying, how do I do this? And I found one person asking, hey, look, I'm sick and tired of finding reams of 87 pages of theory and example code that includes an entire operating system. How do I initialize this blasted thing? And this person said it similar, but he actually offered a sample set of code. If you do this, it will probably work. Not because he says, I don't know if I'm right and here's what I'm trying, somebody help me fix this. I wouldn't want to debug that. But you see this guy down here? This is Etched Pixels. This is the guy that chimes in on the Z80 Retro Discord every now and then. And from his comments, I would be surprised if there's a CPU he hasn't written drivers for. So while this is only an opinion, he's the guy that wrote Fusix and some other things. This guy's pretty good in my opinion. I've seen some of his comments, and I'm like, whoa, there's some insight there. So I like the fact that he thinks this is cool. This would set up 19.2 if you still have problems. Check. Yeah, because the speed could be wrong based on a divisor that we can look at in the manual. So if we just cheat, and I'm all for cheating when it helps me personally, and just paste this in, maybe we'll get somewhere. What I will not do is blindly use some crap without verifying it. So what we'll do is we'll start with this guy's example. I don't know what he's doing. He's got a 33 in hex. That's the number 3 in ASCII. He has an output, and he goes around a loop. It looks like he's just printing a bunch of 3s. And some loop down here. Okay. I don't care what baud rate we're going at, even if it's completely wrong. What am I doing here? Let's go up here and put it right there. All right, let's delete all my junk. Okay. So, shout out to Etched Pixels. Thank you very much. I should have just asked him. What do I do? He probably wanted to watch me suffer. I would. You know, this is actually part of the fun of it. We're going to have enough things to figure out today. And honestly, I've done this so many systems, so many different UARTs and stuff. I do not want to suffer through this morning. I'll suffer through the FPGA. I want to get on the fun stuff. All right, let's boot this sucker up. Now, let's make sure that we at least agree with this. Now, he's got these constants here. I don't have equates for them, so let's go ahead. Throw on some equates. By the way, Etched Pixels also wrote an assembler and a compiler, a C compiler that I downloaded. That's why his name is fresh in my mind here. I talked to him the other week, whatever, about his tools that he uses for Fusix, because I think I'm going to try and use them as we move forward here. This is written to use the cheesy Z8, Z80 ASM thing that I used for the retro. I didn't think anybody would care about that project, and I would be doing it for myself. And I just threw it together because the retro, the assembler I used on the retro is like so primitive. It's more primitive than anyone I've ever used before. And I explained that early on in that series, that I chose it on purpose because it has absolutely no features. Therefore, no one can be confused if it was your first foray into this sort of thing. And I think I chose wisely. I chose acceptably. I'm going to go with that word. And I don't regret it. But if I'm going to do a bigger project, I want a better one is my point. So you'll hear more about Mr. Pixels soon enough. Okay, so what we need to do is put the addresses of those buggers in there. This manual stinks because they don't have a general, like, here's the addresses of all the stuff. I think there's a table in here. Please. Well, what I do know is they're in order. So we can at least try to find them. All right, so this is Control AO and Control A1. So the first thing that I'm going to observe is I don't want to use, well, I could use ASCII 0. The reason I was not going to use ASCII 0 is I don't know. It has modem control lines and stuff on it. If we use ASCII 1, they're not there. But, all right, we'll go ahead and go with the flow. You'll see that between ASCII 0 and ASCII 1, see that bit there? It's different, okay? So if we're going to just blindly take this guy's code and tweak it, we better use the same port. So for control A0, it's at port 0 in hex. I prefer this notation. This is the old way of doing it, the postfix H. So you see that, and down here with the B at the end, you can do that as well. So I'm going to stick with that, modern days. I mean, I haven't used this notation since 30 years ago. So control B0. Do we want to risk it? Find control B0, and it can't. Well, I probably have to type a few backslashes and carets and percent signs in there. Control B0, address 2. Okay, ASEXT0, which is the insane way to match. What do I have to type in to match this, I wonder? Yeah, like I said, a couple of percent signs and an unprintable code. Don't do us any favors, guys. No, don't do us any favors. We're going to need a stat 0 at 4. So 4, no, for stat 0. We're going to need, what's he doing about the received data? TDR0. Yeah, he's just sending. Okay. TDR0. Right there, 6. Whenever anyone's having trouble and you steal their code, you need to check everything, because he could have a bit wrong here or his IO mapping is wrong. So that's great. I'm real excited to see that somebody tried this. They read the manual. They came up with another person said it looks good to me based on something that he did that does work. If this doesn't work, we'll just go steal it out of Fusix. It turns out that Pixels might be on the Discord right now. I have a window around here somewhere with the Discord on it. Here we go. If you're into this stuff, by the way, the people on the Discord are really nice. There's some comments right there. Long hair, yeah. They were kidding me about my hair. I haven't had my hair cut in a long time. I said, yeah, my sweetie came in here with the hedge clippers. I'm not going to get through another day without it. Anyway, so he's giving me guff about my hair. Of course, his icon looks like this. So I don't know if that's what he really looks like or not. Who knows? Anyway, that is, my point is, when did he write that? Oh, that was yesterday. As if he was on, I just saw that this morning, so he might actually be lingering. We could ask him in real time. Bother people on my Discord. Okay, thank you. All right, so we got the transmit data register. We need the EXT. Oh, we were there earlier. They just skipped. Oh, here you go. Right in the middle of the ASCII. Here's what I was talking about. Here's your receive data register. And then right in the middle of nowhere, we have the CSI control register. These were a completely unrelated peripheral. Then we have timer data, and I don't think this has anything to do with the UART. Then there's a timer control, which is like a CTC, and now we come warping back to Mr. EXT0 again, which we all know looks about as nice as this if you try to search for it. So he's not using the Berg. He's using his own clock. We're going to learn all about this when we try to make this thing work. So that's my point. This is 12 in hex for ASCII 0 extendo reg. aux12. All right, this will compile, but I guarantee, well, boy, you know what? Well, it won't compile. What's wrong? Comment expected. Was out 0. Got some atrocity. Line 23. Oh. Out 0. It's what happens up here. The out 0 operand is not in the crapo assembler. I should have upgraded to the Fusix toolkit. I downloaded it and I built it and it goes, and we chatted a little bit about it, but there was a he was updating it. I was supposed to wait another week before I used it, and I haven't given it enough time. I haven't given it the respect it deserves before I talk about it. I'm not going to laugh at his stuff the way I am these manuals. I mean, you know, we're just doing this as hobbies, people. You got these multi-million-dollar international corporations that are doing just this insane amount of work, and they're used so widely that even other countries bootleg them. Give me a break. Fix your manuals. You can afford it. All right, so what do we got to do here? Out 0. Oh, there's a lot of them. I can't assemble that. But I think it's this ED39 is an out 0. And I talked about that before, but I forgot. Here you go. Does not support the out 0. Oh, boy. I suspect we can just do this and put the number in there. We will double check that before we just blindly run this. What do we got? Control A0. Control B0. Yeah, this is going to be hard enough as it is. We got instructions that can't be assembled. We got a manual that can't be read. It certainly can't be searched. Don't be any favors, guys. Easier to design a CPU from scratch in the FPGA than it is to use some broken piece of garbage with seized up FIFOs. Oh, I love it. All right. Neil noticed that this example code writes, it does not read. If you scrolled further down that note, he'll probably say, yeah, it works until the reader seizes up. Okay, so in here you see a comment that says, if the feed clock runs at 38,432 megahertz, which mine does not, then these settings would give you a specific baud rate, because what you're doing is you're dividing this by 30, then you're dividing it by 16, then you're dividing that by 2, and you end up with this. So what would happen is, if we're running it the way it is right now, I'll clip a probe on there to double check, but if we ran, what am I doing? I'm running mine at 25 megahertz. Then I divide that by 2, and I send it in as the crystal input. And then inside the 180, it's divided by 2 again. That is my feed clock speed. So this is 25 divided by 2 is 12.5, divided by 2 is 6.25 megahertz. And then we divide that by 30, and then divide that by 16, and divide that by 2. And then we'll get God knows what we're going to get, but that is what I believe the frequency should be for the bit rate. So what do we get if we calculate this? We're going to get a 6510 bit rate, which is ass. Okay. Now, we can play around a little bit quite easily. Instead of dividing by 30 here, I know we can divide by 10 and use a different value in there. So what do we get if that happens? Let's go ahead and try. Oop. Oh. 2, 2, 10, 16, 2. Wow. Wowie, wow, wow. That's not far from 19,200. That's not on, but what would the error be? If we are 19,200, scale equals 3. If we go to 19,200, divide by that. Did I do it right or did I do it upside down? Oh, I got a 2% error? That's good enough. It would work. Oh, thank you, God. Either way, I can't think. I can't do basic algebra while I'm talking. Wow. I'm in love with you, baby. Baby. All right. Okay, let's do some reading. Wow, this is super awesome. We're running at 19.2, people. Oh, I love you. I love you. I love you. By random happenstance, I think this is close enough that it will be recognizable. Now I'm going to change this to run at 10. Now let's look at the manual a little bit, because like I said, we want to verify that these all make sense. When we get down here, we'll see that one of these bits needs to be flipped, because he had it set to divide by 30. And I know that 10 is one of the options. So let's see what our engineering friend has to say about this. Now, what are we at here? Control A0. And, of course, I can't search for it because there's no way that's what we are. Oh, I can search for 00H. This was how I found it earlier. Not. Boy, I lied. I'm lying today like crazy. Can I at least find ASCII, please? Lordy. Well, let's go ahead and just zoom through here. It wasn't too far in. It was after this stuff, right? Back there she blows. Okay. ASCII data. In fact, it's right there. Okay. ASCII control 0. MPE, RETE, these turn on. A lot of UARTs have these bits that allow you to shut off the receiver or shut off the transmitter. I always thought that was dumb, but if you're using it to talk on like RS-485, you do need to turn on and off your data because they're using a shared serial bus. It's a network setup. It's not a point-to-point. So turning things on and off does it makes it handy for your drivers and stuff. RTS, the MPBRE, I don't know what that is. These mods, operating like how many bits and parity and all that other junk. So let's find the ASCII detail dialog. Oh, it's right here. Oh, yes, the MPE. Oh, luckily, we're not doing this junk. This is the multiprocessor mode, which gets us back to, the idea of having shared buses. If you turn this on, it does weird crap. Leave it off. So bit 7 should be a 0. And it is. He's got a 1 for RE and TE. That says turn the darn thing on, please, because by default it's off. Thank you very little. RTS 0. He has set to 0. We're not going to use it. We don't even care. What do we got here? Okay, so there's bit 7. Receive enables 5. When TE is set to 1, things work. When they don't, it doesn't work. Turn these on, otherwise it won't work. What does it say here? It's cleared in IO stop mode and reset and blah, 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 blah. This is not reset. The previous contents are held. Yeah, okay, nothing leaps out at me right there. Quick skim. This just lets you turn on and off this pin, I think. It's a 1-bit output port. And, of course, it's not automatic in any way, so we don't even care. This is the multi-bit garbage again. error flag, receive thing. Is that an input bit or something? It's also writable. I don't know what that is. Whatever. We don't even care. It is undefined during reset. When written, the EFR resets error flag. Ah! Well, there you go. That's good to know. This might be the dumb that we need to solve for that overflow thing. Good thing we took a moment, right? So anytime we're stuck, I'm going to rewrite a 1 in here. And let's make sure he writes a 1 in there anyway. This actually may not be the actual flag that gets stuck, by the way. But it doesn't matter. If it resets something, whenever we do it, let's have that a 1. So that's what? Bit 3, which he has a 0 in there. And that could actually cause him to not come out of reset properly. If it's in that weirdo mode and he tries to reset while he's going. We should send him an email. Be a good netizen, please. Can I not count or something? I just messed the wrong bit. He already did the right thing. That's bit 3. What am I doing? 7, 6, 5, 4, 3. Right there. That needs to be a 1. That bit over there is RTS 0 and bit 4. Because it starts with 0, right? So there's 3 is 1. He's got a 1 in bit 2, which is part of these mod things. I love the fact that they give you this giant table over here. If you're so inept that you don't know what happens when you set this bit to a 1 to turn on the parity, and this one to a 0 to have 1 stop it, lucky, thank you God, for them putting in a table like this so I can look up which of these enumerate all of them. Why don't you just decide, I want 8, so that's the mod 2 bit, which is where the cursor is. That's a 1. The next one is 0. No parity, and he has chosen 1 stop bit. Now, I'm going to go with 2. And the reason I'm going to go with 2 is because we're not running at the right speed. And what are we doing? We're running at... We're going too fast. So here's the deal. And this actually happened to some of the people that watch these are also playing around with their Naboo boxes. Early on, DJ couldn't get his thing to communicate. And the reason is the Naboo has some weird thing going on with the serial port, and they run it at a goofy speed. And it's slightly faster than a standard speed. Much like this, okay? And when he had that problem, I kind of chuckled, and I thought he was going to fix it in his video. And he was like, oh, I don't know what to do. And he was putting timing and stuff in his code. And I'm like, oh, I've so been there. And it was really an entertaining thing to watch. It was very informative and wonderfully educational if you've never gone through this process to try to figure out how to deal with this. So I sent him an email, and I said, if you add a second stop bit, what you're doing is you're wasting more time between characters when you're sending them. So if you're sending them too fast, and that was his problem ultimately, when he finished a character, he would start another one. And if you're going at very full speed, and there's the key, if you're sending a bunch of bits, and then you immediately start sending the next one, after a little while, a guy who's receiving at a lower speed, the speed it should be at 19,200, will slowly get out of sync. And the bits will get there sooner and sooner and sooner until it's reading the wrong bit. And then all of a sudden everything goes awry. And this is an asynchronous protocol. So what happens is, if you're going slightly too fast, and I'm assuming that we can get away with this, provided that we resynchronize all the time. And the way this thing resynchronizes, I should do a whole video on just on UARTs and this technique. Because what happens is, there's a special, what a stop bit is it's the amount of period it waits before it sends the next byte. By throwing in an extra stop bit, what you're doing is you're forcing the receiver to stall briefly while waiting for the next character. When it stalls, it will resynchronizes to the first bit that arrives in that next character. So as long as that next bit arrives later than it would normally be, if it was running at full speed at the right speed. As long as it arrives a little bit later, the receiver will constantly resynchronize. You can get away with stuff like this, all right? Throwing that second stop bit in, somebody else beat me to the punch. I was so jealous. I'm like, oh, do this. And there's other things you can do too. In his case, the UART has the ability to use like marking and spacing parity. Well, I believe that mark parity is the same thing as a stop bit or space. I can't remember. I think it's marking. I can never remember whether marking is high or low or whatever. But you can set a parity to a constant value and just say, make the parity bit be the same voltage as a stop bit. Then you can select 2 stop bits and end up with 3 stop bits. Okay, so you can waste time automatically between characters, my point is, without putting software delays in your code, which is error prone. He got it working, but it was running much slower than it needed to. And adding an extra stop bit helped him immensely, and things ran much more smoothly when it did it. So anyway, I'm going to add that extra stop bit because I know I'm going too fast. So this will be a way around that. Like I said, I should probably do a video on how UARTs work. It'll make a lot more sense if you got into that. I'm going to also look up the ED39 because I'm making a real big assumption there. And if I'm wrong, let me find my manual here. Come on, where is it? Documentations. I gotta find my Z80 stuff. Actually, I need to find my Z8S180. Where's my... Here we go. Actually, I think that's the manual that I just had open. That's this data sheet here. Here's the family. Maybe the... Oh, I don't... Does it have out 0 in here? It does. Out 0 instruction. Here we go. I talked about this before when we were using it because the Z8S180 has a 16-bit address bus for the I/O ports inside of the chip, and you need to specify that the most significant 8 bits of the I/O port address is 0 or it won't work. And some of this is reconfigurable while the thing is running, which I didn't do, and in the default mode, this is what you need to do. Out 0, MG, well, that MA, that's out. So what this is, I think you can put any register you want in here. So they give you, what, 3 bits? Yeah. It allows you to specify which register you want to put in there. The address, the I/O address, comes last. So this here is what? That'll be an ED. It'd be nice if they gave it to you in hex, which they don't. But, you know, ED, all right. Then the 39 includes the accumulator register in this field in here. So the A register must be 11, or rather what, 39. It had to be a 111. It would be a 7 in that G field over there. So somewhere in here it'll say A is this. Oh, thank you for not putting it on every page. Yeah, no engineer ever saw this manual or was involved in the printing. No engineers were harmed in the production of this manual. You suck. Oh, there we go. Address values. Bit values. Pretty sure the accumulator is 7. There it is. All right, so that's correct. And I've seen it enough times to know how they do those encodings. If you're not used to this, that could be a day right there. Okay. So ED39 means I'm going to use out zero instruction with the accumulator over here. I could output other registers if I wanted, is the point, in which case that value would change. So that's what we verified. And every time he uses the accumulator, so this will work. We're just assembling it ourselves. And I assume these are all, yeah, those will work, I'm pretty sure. We can look at the bytes over there and the output of the assembler to verify that it did the right thing. Okay, so what do we got? We got one register in an hour's, oh, trust me, once this goes, everything else should go real fast. He says with great confidence. What's this one going to do? We have control B0. What do we got? This is some sort of multiprocessor mumbo jumbo garbage. We don't care. We just need it to not be on, or the mode is not on you. When set to 1, it does all kinds of crazy, stupid stuff and annoying things. When it's 0, it's reset. Done. So the most significant 2 bits, make them 0. There we go. Then we got a 1 down here. Clear to send prescale. Now we're getting into this divide by 10, divide by 30 foolishness. And you're playing with that Woody Allen bit here. On odd-numbered Thursdays, when you wave a fish over your head, for channel 1, it's multiplexed with the RxS pin. Thus, this is only valid when you got a 1 in this other bit in some other random register, and the CTS pin function has been selected. The read data of this is not affected by reset. If SS20 is not set to this, and the Berg mode is in there is 0, then writing to this bit sets the prescale control. Under those circumstances, a 0 will divide by 10. The prescale function, while a 1 will do a 30. This bit resets to 0. Now, is that perfectly clear to everyone? Well, he's got a 1 in there. And it says if, then, else, and God knows what all these other conditions mean. And there's a 1, it's divide by 30, and that's what that guy's doc said he's doing. So I'm going to make it a 0 and blindly assume I'm going to divide it by 10. Now, I'm pretty sure that what happens, first of all, this Berg thing is off by default. And it also says if the SS2 are not 111, and this is 0, then writing to there does this stuff. So all we need to do is make sure that SS0, 1, and 2, which are in this register, are not set to this, and we need to make sure Mr. Burgermeister over there is set to 0. And I think it is by default when it comes out of boot. So let's see here. What do we got else after that bit? So I just made that one 0. We got 4 more bitsicles. That gives me bit 3. There's the even odd. We don't even care. Divide ratio. Okay, this is the thing that says if I want to divide by 16 or 64 or whatever. You can divide by 1, but again, watch a UART video somewhere or wait for mine. You want to divide by 16. Or you could use 64, but you don't want to use divide by 1 because reasons. Okay, so when it sets 0, divide by 16 in bit 3, okay? So where are we at? We are on bit 3, is 0. Again, with this other if then else, the X1 and the EXT and so on, we need to make sure that the EXT stuff has zeros in it. And I think it does when it comes out of reset. SSL, okay, these guys. These things have to do with selecting various divider ratios and things like that. There's your other thing. He's got a 1 in there, which he has a divide by 1. Okay, so this divide by 1 is different than this one. I'll save that for a UART lecture someday. Sending or leaving them as all ones makes sense only if the clock A has done this, blah, 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 and you got a moose on the trunk of your car on Thursdays when you're crossing the Washington Bridge. Okay. We're good, I believe, for reasons. Now, there's your overrun, red rough. This is the receive data ready. And that's your transmit data. Receiver empty. Okay, and these IE bits turn on interrupts. We don't want any interrupts. Okay, let's make sure he did the right thing in there, and then go on to Mr. EXT. Oh, here is EXT. It is the next one. All right, so I'm happy with that. It's recognizable. No CTS, no DCD, no break. Just shut off all the modem crap. Okay. And that's going to go into ASEXT0, which we know cannot be found by any searching system known by humanity. We just got to keep going until we find it. Random timing junk in the middle of the UART stuff. There we go. And we're back. Oh. Oh, okay. Let's look very closely at this diagram, and then let's look very closely at the same one over here. Oh, boy. Let's hope that we can search for EXT. And maybe not. ASCII, EXT, AS... what do they call it? ASEXT. Hey, there you go. Oh, there's the table with the addresses. Thank you. So if we had to come back and find them, they're in the user manual. Okay. God knows it'll find it. This is I love this math. Oh, let me ask you, what does this mean to you? Specifically, what is that operator doing there? I ask you, what the F? All right, let's look at these bits. All right, so that's not while I was laughing earlier. The reason I was laughing earlier is because in here somewhere, when it documents the EXT bits, those bits have values and meaning, and it says absolutely you need to set them to certain values or it won't work. Oh no, oh no, oh poop. Wow. What is it? 12 hex? Okay, so that's EXT0. Here we go. See this right here? Okay, that's okay. Look very closely now. These are supposed to be the same thing. One of these things is not like the other. So in this one, that's the yeah. He didn't call it the EXT. He calls it the extension control. That's why you can't find it, because they didn't bother putting the acronym in it. And consistency is of no point in non-literary works, right? I mean, these stupid people. Okay, this red rough thing going on over here. This actually this. Red rough interrupt inhibit on. So you set this to 0 to turn on the inhibit. Now, I don't know about you, but I would have just called this interrupt enable. If 0 inhibits the enablement and 1 does not inhibit it, why do you just call it enable? How many negatives in a row can we line up? Okay, so auto reset, this is 0. And 0 means I don't want to generate interrupts, but as written by the only person who never wrote a program in their entire life, who decided to name it in the least sane manner. Okay, that's what's in here. We need to make sure we get that right, or we're going to end up generating interrupts and stuff like that, and bad things happen. So what do we got? DC D0 disable, disable. X1 is the thing that we saw earlier, and it said that has to be set to 0 in order for reasons for the other things, my other assumptions to be true up there, okay? So what are we doing here? We're writing in a 0, and we got a disable, disable. These are 1 to disable. That's 0 to inhibit the enable. And then we have the X1 bit, which the earlier doc said, if that's 0, then the other notes are valid. If this bit is 1, the clock is taken from the Berg, or the clock A pin is taken as a 1X clock. Yeah, the isynchronous mode, I think the world calls, you pronounce that isynchronous. Isochronous, I would say that if I wanted to sound like a clown, but I think that's also tolerable. It's like me saying solder. I know everybody else says solder. I can't say solder. And the reason is because when I was in junior high, back when, junior high had shop classes and metal foundries, sheet metal, lathes, and we had a whole foundry and stuff. And we learned to solder and everything else. One of the kids in the class insisted on calling it soldering, and they were being very obnoxious about it. So to this day, I can't say solder. I sound like a pretentious 7th grader to me. When I say that, so I can't. I've been psychologically damaged by some loser in junior high shop class. But you know what? He's probably was right, but he was such a snob about it. To this day, no, I'm not childish at all. Oh, just shoot me now. Okay, what's going on here? Yeah, someday I'll talk about UARTs, and we'll learn more about that if you don't know already. Clock A pin, blah, 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 to obtain all this other crap. And, there we go. If this is 0, I was looking for that, then the clock from the BRG or that is divided by 16 or 64 as per the DR and the control B, which we already did. To obtain the actual bit rate, this mode received data on Rexa is not required to be synchronized to a clock. And this is so poorly, it's true, but so poorly phrased. If you don't really know, if you haven't gone through the real, if you don't really know what UARTs do and how they really work inside. First of all, they could have been a lot simpler, but no. That's just written so poorly. Anyway. So there's my X. It's a 0. Then what do we got? We got the Burgermeister over here. If those things are set, if SS2, the control B are not 1s, and this is 0, then the baud rate divides phi by 10 or 30, depending on this, and we just change that to 10. If SS2 are not 111 and this bit is 1, then the Burgomeister divides phi by twice the sum of the thing in there, and divide by 2. It'd be easier to redeem coupons at some of these stores than it is to go through that. Bottom line is, we don't put a bit of 1 in there. We put it 0, and we recognize this from we're clowning around with the control B register. So I think we're good. Break enable. We do not want to have break conditions reported or detected or anything else. That's bit number 2. He has that set to a 1. 0, 1, 2. Well, it won't hurt anything, I guess. If this bit is 1, the receiver detects break conditions and report them on bit 1. I'll overlook that, right? Comma. And the transmitter sends breaks under the control of bit 0. And, given the vintage of this, I don't know if these are translated from foreign language to English by, Google Translate in the state that it may have been in 1995. Google didn't exist, but you know what I mean. It would have been Alta Vista Translate. This is so horrifically bad. I'm amazed. Okay, but I suppose we can discern meaning out of it. Break detect 1. If the receiver sets this read-only bit to a 1 when it finds a break. It's cleared when you write a 0 to the EFR and Control A. That might have been the thing that we looked at earlier. It's also reset by IO stop and some other junk. Okay, great. If this bit and bit 2 are both 1, transmitter holds it low to send a break. So that, I didn't get that out of this one. This is so bad. Okay, so what did this guy do? He set 110. This is a read-only bit. He may know something I don't. Because he wrote a 1 into it. Wow. Break, enable, break, send break. Well, as long as we inhibit the interrupts by writing false into the inhibit bit, we're fine. Then what do? We set 0 and we go to stat 0. It should take me an hour to find that one. Those are the timing values, I think, if we need to use the Berg and the math. And this one, that was written by someone that actually passed an algebra class and didn't put an extra multiply operator in there. Oh, proofread, people. Proofread. Okay, what's this stat 0? Oh, look at that. I accidentally stopped on a page. Oh, by writing a 0 in here, we're clearing this stuff. RE and TIE. Receive interrupt enable. No. Transmitter. Okay, so no interrupts. Got it. Okay. Probably okay. Now, we got to go back to our resetting of the stuff, which I, like an idiot, didn't write that down. We needed to clear something. I'm just going to see if anything leaps out. What did I do? Poopsicles. It was in one of these. I'm going to change this comment. And replace it with that. I'll be nice. Stolen from okay. Well, we're writing, we're not reading. I'm going to have to say beware the ides of the errata. The ERF bit in Control A. Alrighty, that's the, well, you can't have transmit over. Well, in theory, I guess you can. All right, now we're going to do this. He's going to go to C out. Do I have a stack? So you got to be careful because remember, this doesn't do much. We got to load a Stechamus pointerus. Or not call a subroutine. Maybe it'd be easier to just inline this. No, because I'll move on to something else. call C. All right. How do you set up the stack pointer? Okay, dingus. The thing is, I don't think you can just say load stack pointer, because it's never something you do very often. I think what you do is you say, put it in the HL register, and then you copy it in from there. So let me open up another window. Is working with only one terminal. I don't know how I survived back in the old days. I'm lazy. I'm going to steal it from my boot code. It must do it in here. This is where we're heading anyway. Wow. I'm going to miss my lunch goal. You know what? I will be happy if I get this stupid UART to print something. Where do we do the... Oh, look at that. You do have the ability to load. They wasted instruction on that. Interesting. I find that surprising. I mean, it doesn't matter how inefficient such a thing is, usually, because you're only going to do it like once. All right, what are we doing here? We got to keep in mind, this is all going to run out of this FPGA ROM simulation, and I'm not going to bank it on and off until we get everything else working. So I'm going to just load the stack pointer with, actually I could just put 0 in there, and what it will do is it will wrap, as soon as you push it'll go to FFFF and work its way down. And the neat thing about that is, as soon as you push something into the stack, you'll see one of the byte values on the LEDs. We should be able to know what's going to happen. What happens is, this is going to call a subroutine, and when it calls it, it's going to push the return address will be the address of this jump right here. And the, the low byte will go in first. So the least significant byte of the address where this jump opcode is should be the thing we see on those LEDs. And the rest of the stuff that the stack is used for will go below that. And it'll come back here, and it'll actually, the LEDs should freeze in that pattern. It's not like it's going to change over the course of time. And the reason for that is we only call one subroutine. We come back and call it again. So once it's set, it'll stay there. So that'll be a little sanity check of our app. And let's see what happens here. First of all, seriously? Oh, we got an N0. Whoops-a-daisium. I have to figure out what that one is. C4H, whatever that is. Did I put that in already? Stat 0. Yes. No, I gotta look up this opcode. TB. It'll be similar to the one up there, most likely. This will be after the first 2 bytes of whatever N0 is. Find N0, please. We get to have this fun again. All right, so we got this bit pattern. Now, in theory, I could do it like this. Put a B after it, or a 0B in front of it. Possibly, if they support the 0B leading prefix model. And you see down here, it's 00 followed by G and 000. We know that G is A, and A is 3 1s. Oops. So that should do it. 00, 111, 000. All right. And it with 2. Okay. Now this assembled the code, and then it built it into the boot ROM that we saw last time. So let's look at the listing here. The odds of this working on the first try is insanely low. There should be a 23 on those LEDs. And remember, the LEDs light up when there are zeros on there. So this should look like on, off, on, and then on, off, off. once we do this call instruction, because that is the address that will be pushed for the return to go back to. All right. So what am I thinking now? Let's scroll up and make sure that we have a sane output in here. And by that, I want to look at if we have block RAMs in use that makes sense. 8 of them. I needed 4K, and each RAM is a half a K, so that makes sense. When we did it last time, it used 1. I'll let you go back and watch the other video to remind yourself of that if you forgot. And if I'm wrong, we'll just ignore that fact. All right, so in hex, we're up to 33. We don't even need 256 bytes to do this. That's fine. This should work. What am I missing, people? I don't know. What I'm missing is I stopped the the camera's still rolling. I stopped the capture because I didn't want to waste 5 terabytes of disk. Well, we're not using that camera. We're going to put on D, the next letter unused. Alrighty, let's go back to the bench camera. Oh, I can see what? I can see it on the screen. Let me turn the light off so we can see the LEDs better. So now it's really dark over there. Make, I added this to find, make prog. That's what I want to do. Make the progy wogy. Let's see what happens. The LEDs are off. We're downloading. Please be a 23. I don't see nothing. Oh, it didn't run yet. All the LEDs are on. Well, okay, time to turn on the scope, because when this is running, I believe that this clock, see this thingy right here? That should be available on one of the pins. Now, I don't know if it's enabled or if it's shared. Let's see if we can search for that. And of course, you have to type in that magic value, which doesn't even exist even when I copied it out of the document. Lovely. But I can get to CKA by using that pattern, because, you know, it's just intuitively obvious. That's 1D, whatever that is. We need 0. Okay, that's a shared pin there. Let's just go back and look at the stinking pins. Let's see if it's shared. CKA 0 is shared with DREC 0. Boy. That means we need to make sure that it is set. There we go. There's the ones. If you're doing this, then the CKA pin is used as an input. But I believe if you're not set to triple ones, it becomes an output. If you're not, and the mode is 0, which we did do, then these bits specify something in there. Setting of these bits to this sense for channel only when it's selected, or the function offers this when bit 4. That offers the CKA1 function when bit 0 is what? Offers the function. That might mean that it outputs in there, but I don't know. I offer you the function. Have a sandwich. Okay. Why don't we do a little more searching? Well, system config register, which is a whole nother thing. Okay, here we go. In this mode, the received data on the RXA does this, that, and the other thing. In this mode here, the Burgermeister B is not set to ones, and this bit is 0, which I think we have, and we went to divide by whatever. Clock is presented to the transmitter and receiver, and it is output on the CKA pin. Yeah, baby. It is offered. The function is offered. And that's definitely a loose translation with no proofreading. And that other statement there. So the question is, how do we get that stupid DREG 0 stuff out of our way and make sure that we have, maybe clip a probe on there and see what it's doing. DCD 0, that's for clock 1. Clock 0, which is the one we care about, because it's the one that's offered. It doesn't say. Come on. Oop. I missed something. Yeah. Drive capability. It's a drive strength changes. I don't care about that. It's just, it's good enough. Okay, CKA, there we go. During reset, this is initialized as that. If that bit, that's for CKA1. During reset is initialized A0. If either of these in the DMA mode run is done, as long as I didn't do that. Now, I'm assuming I did not do that in the code that we were looking at, which could be a complete foolishness. See this? That might be a DMA thing. Well, let's look and see what's on address 32. DMA mode. I wrote to decontrol, which might be DRAM or something. I don't know, but let's look it up to make sure that's not going to bite me in the butt. I think they say 32H or not around when they use the ports. So about DC, was it NTL? D? Oh, lovely. It's not in here at all. DCNTL. Oh, but I need to know the magic random letters. Okay. DMA weight control. Yes, okay, there we go. As stated. Where? Well, which bit do they care about? I forgot what I was looking at. Now I lost my page. Dag nabbit. What was it? It was a CKA0 jazz, which we probably can't search for either. Come on. Oh, we're young people. And of course it won't find it. Just shoot me. Oops. Actually, that's where we're at. Okay, so when DMA mode has to be set to 1, it uses that. So the DMA mode, which allegedly is in here, DMA mode. All right, that's the bottom bits over there. I set it to 0. Okay, fine. All right. In theory, then, the clock should come out of the CPU, and we should be able to see it on our scopage. All right. Okay, so here's my chip. And where is ZKA0 right there on pin 50? The question is, did I route it over here? No, I did not. I routed up here. Right there, pin 12 on this handy-dandy header where I should probably solder some pins in anyway. All right, let's go have a look-see on ZKA0. Alrighty, we go this one. Okay, Mr. CKA0. Let's zoom in a little bit here. Here we are, CKA0 right there. Turn on ye olde scope. All right, here's my prober. Clip this on the grounder. Okay. I wonder if I can do one of these. No, it's too far in. I could probably stick this in the holder. All right, I got great news. There's absolutely nothing on the scope. It's high. I'll do a screen cap. I don't have my usual USB. Whatever. It's pulled high. And I see no clockage. That really reeks. As I poke around in here. Oh, this is just awful. Awfulness. Oh. All right, so much for my 3-hour port. Because the blasted UART's not even working. Well, you could try pinging the Pixelmeister. What I should actually do is make sure the code is running. Because we did change a couple of things, right? We changed the amount of RAM that's in the FPGA down here that's being accessed by the CPU. So there could have been some screwy, there could be something going on with that. What am I doing here? This is the first time we tried using the stack. I mean, who knows? Well, what if... All right, let's load this stack pointer with a little different address. And the reason is so that I can just write up at the top of memory random values and put them on the LEDs. Let's put accumulator, which I think we can do this, because in 8080 that's like STA or something like that. I think that's a valid instruction. Point is, we should see the 33 on the LEDs. The LEDs are currently set to all zeros right now. Of course, I might have the address order backwards. Does it put the least significant byte in the memory first or the most significant byte? When it's pushing, it works its way down, and the memory is always backwards. So the least... Oh! Of course it's 0. It's supposed to be 0. it might actually be working. But what it is not doing is outputting any data, number one, and number two, the clock is not coming out that pin. So something's going on with this. This is like I said, this is you spend 1,000 hours getting these values right, followed by nothing. Now, what I could also do is go back and recopy that guy's code as he had it. The reason I changed it was because my clock is running at a different speed, and I wanted to use the different dividers and whatnot, okay? So if we leave his the way it was, I got all these things, these out zeros in here. Let's put his in here. Here's this first line. Oops. Right? So here's what he had in there, and I changed that. Okay. Then he puts that one in there. That's mine, rather. Here, let's put some spacing in here. See what's going on. His second load is this one. Now, I don't believe his goal was to have it come out on clock A anyway. Oops. By the way. So we may have something. I may have something wrong with the assumption about the fact that clock A would have anything coming out of it, or the TXA or whatever that pin is. Here's his third load. Point is, if we do this, we should see serial data coming out of the thing. You gotta have the proper alignment, What else do we got here? I always change multiple things at a time, and by that I'm referring to this. Okay, let's program this up. So two things should happen. The rate should just slow down a lot and do some really worthless bit rate. And we should see a 33 on the LEDs. Oh, yeah. Hey! We got the 33. So that means that the thing did not crash. Oh, I'm seeing a clock. Whoa! All right. So the pixel guy was right. That his code doesn't stink. Mine does. Thank you, Etched Pixels. Okay, now that means mine is bad. What I need to find now is a nice bit of a USB stick so I can show you these pictures on the scopage. Here we go. Let me throw this in here. I do not want to go back and edit this darn thing, but I will to put these images in. What am I going to do? Print, save, wash, rinse, spin. There we go. That's ping number 35 for future reference when I'm editing. Okay, what do we got on there? We got 104.167 kilohertz. All right, what did I want to do? I want to redo the math here. He's doing that. Now, my math could be wrong, but the only thing I tried to change, was that 10 from the 30, and my frequency's different. So if we take, here's my other terminal that I had up here. Well, here's the one for the camera. If we say that, I believe the clock, I should have seen a clock of that frequency, but I'm running his code, which does this, which is 6510, and that is not 104 kilohertz. What am I doing wrong? Ah, that is, okay, that's not the freaking, oh, that's the bit rate. He's in divide by 16. So he's either looking at this, oops, or he's looking at this, which is the frequency on my scope. Yes, okay. But the reason I removed this divide by 16 is because that's done on another part of the circuit. So the clock speed is this. The bit rate is that over 16. So my math actually is off anyway. However, it doesn't matter. I got no clock at all. So I did it wrong, but I should have still seen a clock. What I should have seen was this on the scope. And I saw 0 hertz. So I broke one of these settings. His is definitely generating this frequency, which is 16 times the bit rate, which is very normal standard procedure for a UART, and especially since we have the 16 divider going in the UART configuration. So okay, so what I'm going to do is I'm going to leave this one alone. As we dorked with this, what did I do? I played with these bits. I don't know what I did up there. Let's take this one off. See if we can get the right speed. Did I change this one in any way? No, I did not. Those two lines are the same, so I'm going to get rid of that. All we're doing here is taking that bit off here. All right, let's... You know what? You know what else is really annoying about some designs? Remember when I set a bit in here and I said, oh, we'll be resetting something? You may have to write back in a second time to turn off the reset bit. Sometimes peripherals have that feature about them. Let's see what happens here. And you may recall the reason I was clowning around with that was because of that overrun seizure problem. All right, let's run this make probe. Fingers crossed. Camera recording. It'll be E. Oh boy, what do we got now? All right, I reset the board and my scope changed to 312,500 kilohertz. That's ping number 36 for future editing, which I probably won't ever do. BC, what do I say, 315? 312,500. It's very close to the right speed. Now, if the clock is running, I'll bet that reset thing is related to the problem. Okay, so let's see what's coming out of TX0. It's bit bopping. We put it in a single scan. Now, unfortunately, it's writing out continuously. It's writing 33 in hex out. So I should see a start bit followed by a 33 followed by 2 stop bits. And not sure that I'm seeing that. We need a bigger delay between the times that it writes the data out. Because I'm not seeing that. That's ping 37. But we're getting data. This is crazy cool. I've spent a lot more than 2 hours getting a UART to work before. I can assure you of that. I'll bet someone out there holds the record. How many days, people? This can get ugly. Okay, so what this means to me is that I was right about this register, and dividing by 10 versus 30 is cool. So that's okay. So I broke something up here. What did I do? I messed with more than one bit. That's Control A0. Rink! Control A0. Where is it? Come on, buddy boy. Control A0. Right here. I was clowning around with the mods, and I think I probably left EFR on. I'll bet I'm supposed to turn that off. EFR is the fourth bit of 1, 2, 3, 4. He had a 0, I put a 1 in there. And he has 100, and I put 101 on there for the mode. So the mode, I put an extra stop bit in there. And that actually does match my screen. I forgot that this was in the register that, oh, okay, no, that my scope was sending 33s. The problem is, if you only send one stop bit, I was looking for 2. So the problem is that this bit needs to be a 0. Which is even more annoying, by the way. Because if we're supposed to set this bit to reset the overflow, the overrun error, we got to remember to set it and then unset it in order to, toggle it, which is annoying. Quite often systems that have resets will allow you to do the reset in a single write operation, and it will trigger the reset if you write like a 1 in there, and then it otherwise, it clears it on its own on the next clock tick and so on. So let's just go for gold, make it and prog it right up here. Now the funny thing is, this doesn't generate a reset on the CPU, so the CPU is running the whole time when I reprogram the FPGA, and I'm sure the CPU crashes. So let me hit the reset button here, and it's not doing anything. That seems weird to me. Okay, no, okay, there it goes. It is. I had my scope in single shot mode. Okay, single shot mode. Alrighty. But the scope pattern did change. That's ping number 38. It changed where I can see what appears to be a start bit, because it's the only time it's low for 1 bit time. 33 is up to, down to, up to, down to, and then we have 2 stop bits, which are high. Yeah, that is correct. We have our 2 stop bits, so we have control of the UART. Well, that means I should be able to just shove this UART, or the USB adapter in there. If I just put some wires in there, we should see a bunch of 3s. Let's make that happen. Well, what we need to do is power this down. I'll do a shutdown. Yeah, this is just what I need. Someone's cooking something that smells real good in the kitchen. Yeah. Okay, so this is powered down. I should be able to unplug. Turn on the old soldering iron. Oh no, I'm gonna have to dig to find a header to put on there. I haven't unpacked enough stuff to know where my headers are. I'm gonna pause and go find out what's in the kitchen. I'll be back in a few minutes.